Well, I'm in an interesting environment. Let me show you a little.
Okay.
Uh, I'm in a
Should I turn
I'm
off
in a
the
shop
recording?
right now. Yeah,
Ah,
yeah, yeah. I'm in a very different environment, so I will close the camera, but
yeah, no problem.
I will be listening.
Okay, no problem. So, all right. So, yeah. So today we're going to talk about structural testing, as the name is implying there. I can go ahead and share the slides again. I apologize for getting the slides up much later than normal this week. We had the oh, what is it? We had the exams, the midterm exams for the undergraduates, and so I completely forgot to upload these slides at the beginning of the week.
Actually, I have a question about the midterms. How do you think the midterms went for the graduates? Was it like all the midterms were copy paste of each other, or
Oh, you mean for the undergraduates, for the licence için, right?
evet, evet, lisans
Yeah.
programı.
Uh, I, I don't know. I haven't been able to take a good look at it yet. At the exams, mine were yesterday. Both of my exams I gave were yesterday, so I haven't had a chance to look at them just yet. Uh, but we will see. I mean, I who knows? I'm sure that some students, because of our current situation, uh, felt that they were it was easier, to copy than normal, since it wasn't a face-to-face exam. But we'll see. At the end of the day, uh, if you copy from someone else, you're not really hurting. You're hurting yourself really, because you know, uh, for me, it's like, when I go to get a job, like when I went to go apply for a job after I graduated, they want to know that I know what I'm doing, right? They don't care so much, whether I passed certain classes, but they want to know, is this guy able to do the job you want him to do? And if you've cheated, if you've copied, and if you've gotten good grades by copying and and taking answers from other people throughout your university years, then when you may get hired for a job, but you won't be able to do the job, and it'll be pretty quickly that it'll be found out, and then that looks bad on you, that looks bad on your university, that looks bad on you know lots of people. I mean, it looks bad on lots of people that you don't want to hurt. But anyway, but I understand why uh, some students might want to do that or feel the temptation to do that. So, but we'll see. So, okay. But as for this, is like, I mean, it's going to be really hard for you, Alper. Sorry, it's going to be very hard for you, Alper, to copy off of anyone here in the class today, since you're the only one here. Uh,
Yeah.
so, uh, anyway, so the idea of the testing is kind of like, if we go back and we kind of think a little bit again about what testing's purpose is. So we talked about how you can't test everything. Like, you will never be able to every possible input uh, for every possible output. Just take, for example, if you were to say, like, if I look up, what is the size of, um, let's see, is Java, in Java, for example, an integer is 32 bits, right? So that means that there's 2 to the 32.
Are you showing another window right now?
Oh, I looked it up on my own, but I looked it up. I did pull up a Google search, but just to look it up. So, but what I'm saying is that in Java, an integer data type is 32 bits. A long is twice that, is 64 bits. Uh, so just if we were to say, okay, I want to test this method that takes an integer value, and I want to test for every possible integer value, Well, if you want to test for every possible integer value, you would have to have 2 to the 32 test cases just for that one parameter, right? So it's quite difficult, if not, I would say impossible, to test systems for every possible input, right? I mean, even a Boolean expression, even a Boolean value, true, false, you're testing, for every Boolean value you have, that's 2 test cases right there to test every possible value. So the idea behind kind of structural testing is helping us figure out a way to design our test cases so that we can have confidence in what we are in confidence in the systems that we are developing. So the idea is the structural testing is based on the idea of paths through a code. So we talked about this a little bit last week. Actually, we talked about it quite a bit last week, I believe. The idea of this path coverage, the graphs. When we talk about graphs, that every decision, every if statement, every loop results in separate paths. So an if-else will result in 2 paths. All right, one where the if is true, and one where the if is false and the else is taken. All right, and so that's 2 different paths that we want to be able to test both of those. Now, that doesn't mean that we have to test, again, every possible value that makes the if statement true, or every possible value that makes the if statement false. But we do want to at least get a test case that follows the true path and one that follows the false path. All right, and so so the more that the paths are exercised, the more that we have a test case that follows through a path, the more thoroughly we can consider the code segment to be tested. Remember, one of the things that we're trying to do is we're trying to help our customers, our users, believe and have faith that we have done a good job of finding any defects that may have existed, and of course fixing them. Obviously, we don't want to just say, yeah, we found all these bugs and they're still there. We want to say we found these defects and we removed them, and after we removed them, we've run those test cases and now they've passed. All right, so that's what we really want to be able to show them. So one of the things that, if you look at the assignment that I posted, and we talked about the examples in the 9H examples that I posted last week, there was this computing this P star, this path, syntactic paths, a number of total what's called syntactic paths. We'll talk about that. This P star. So you want to calculate P star. We'll talk about how to do that in just a moment. So the idea is, it's not just about what are the number of paths, but also what are the number of distinct paths. So let's give some examples here, because I may get too confusing if I try to explain too much. So the idea here is so don't think of M1 so much as a single node, like a single line of code. Think of it as, so like we see here, it's represented by a method. So if there are multiple paths inside of that method, then that will be denoted by this PM1. So it's like inside of method 1, what are the number of paths that are represented inside of method 1, where method 1 may have some if statements, it may have some loops and stuff like that. So whatever the value is for M1, we multiply it by, so if it's in sequence, we multiply it by the number of paths for M2 and multiply it by the number of paths for M3. Okay, so it's X times Y times, it's the number of paths in M1 times the number of paths in M2 times the number of paths in M3. If you've ever taken a probability or statistics course, this should look pretty familiar. It's the concept of choosing, in a sense, what are the number of possible values that could go in the first box times the number of possible values that go in the second box. What what's it called? In probability, it's called the independent events. So it's like if you had M1 represented the flipping of a coin, M2 represented the number of another flipping of another coin, and M3 represented, maybe instead of a coin flip, it's the rolling of a six-sided die. All right. So you would say, what are the possible outcomes? Well, heads, 1 is an outcome. Heads, 2, heads, 3, so forth. But we don't just count them up. That would take too long, especially as these get higher numbers, like what if it was 3 six-sided dice. So here, the flipping of a coin, there's 2 possibilities. The flipping of a coin, there's 2 possibilities. The rolling of a six-sided die, there's 6. So what are the possible values? We could have 2 times 2 times 6. Okay, so in this particular, though, as it relates to software, as we're saying, if there's 2 paths, there's a single if statement. So there's 2 paths in M1. There's 2 paths because there's an if statement in M2, and maybe there's 6 paths in M3. What is the total number of paths through all 3 of them? Well, it could take 1 of 2 branches here times 1 of 2 branches here times 1 of 6 routes here. So it'd be 2 times 2 times 6. Sequence does that. Okay. Now, so that's if we do it in sequence. We multiply the number of paths times the number of paths times the number of paths. Okay. Moving on. So here, if we have a decision situation, an if statement, we'll get into loops. This is not loops. Let's talk about loops on the next slide. So a decision would be, well, if we take this branch, however many paths there are here, we get over to here. If we take this branch, however many paths, well, now we add them together, because if there are, let's say, 3 possibilities over here in M1 and 2 possibilities in M2, well, we need to add them together, because we could take M1 for 3 different ways, or we could take M2 for 2 different ways, or we could take M3 for however many different ways, how many different paths. So we add them together. So this becomes an addition situation. So we add the paths representing M1 plus the paths for M2 plus the paths for M3. Okay. All right. And we kind of do that, as we sequence them together. So if you have a sequence that includes a decision here, so let's say this is 1. This was a decision that had 2 paths. This was just a regular line of code. But then we would get 1 times whatever this is, it's a decision with 2 paths, so we call it 2. So 1 times 2 times 1, which would end up being 2. Okay. So here, if we have an iteration, a loop, there's 2 different types of loops, though. There's definite iteration, where we know how many times it's going to execute. So if we were to say, I want to add the numbers from 1 to 10, right? And I want to do that using a while loop. We know that's going to execute 10 times. The loop is going to execute 10 times. Okay, so if we know how many times, right, it's going to execute, then we consider that as x to the number. So whatever the paths inside of M1 is, right, to the power of y. Okay. So it's going, and the reason, and part of the reason why is it's each time through we want to say this represents a different test case, or a different set of test cases. But what if we don't know how many times it's going to execute? Well, we know it's going to execute 1 time, maybe 2, maybe 3. Well, then each one represents its own independent event. So now we're going to do, okay, x to the I, x to the low value, plus x to the next plus x to the all the way up to the high value. So if we know it's going to execute 1, 2, or 3 times, we'll see this in an example. There's some examples that I've pulled up that we'll look at the end of the slides here. All right, so if we know it's going to execute 1, 2, or 3 times, then it's going to be this to the 1 plus whatever this is squared plus this to the third power, and we add those up together. Okay. And again, what we're trying to get to is we're trying to get what's called an upper bound. We're trying to get a maximum number of test cases that we would have to have in order to feel like we had path coverage, what we call path coverage, complete coverage. All right. Now, when I say upper bound, that means that basically we wouldn't need more than that to really cover all the possible paths that this could take. It does not mean that that's how many test cases we have to have. As we're going to see, for some very even simple code, we could end up with somewhere in the neighborhood of 17, 8. Like there's an example that we'll see here in a moment that has like 17 is our path arithmetic, is our p star value. But the code is relatively simple that you wouldn't really want to, you would barely want to have half of those really to feel like you had tested it thoroughly. All right. So if we have an example here, by the way, there's 2 different ways that I've shown this. One is like this, and one I've kind of taken the liberty to draw this out. When we look at the example on the PDF, you'll see that there's some of this symbolic notation used. And the idea of what it's trying to show is, so this is kind of the start of a code segment. This is a decision situation, so an if statement to show that there's one of 2 different paths that it could take. And then this is a loop structure. So if there's a for loop or a while loop, and like in this case a while loop, move that down a little bit. It should be the top of this should be right up in line with the while loop, not there. Okay. All right. So when we draw this out, it helps us to symbolically visualize what this code might look like in a flowchart notation. All right. And what we can do is we can take this and we could redraw this as our graph. And then we could find out that, so we have segment 1, condition 1, segment 2, segment 3, and 4, and condition 2. And the way that we would draw this, let me do this. I'm going to do this and this. I'm just going to share my desktop. Okay, so here, what we would do is we would say, okay, we have this S1, and my drawing is going to be terrible. Okay, my handwriting is terrible, so I hope that will not be a problem.
It's okay.
All right, so then we would draw another node to this C1. All right, and then C1, this is going to result in 2 possible paths, S2 and S3. Okay. They both kind of come back together to this S4. Let's see, and then, oh, we got this condition. I'm going to draw a little bit off the line here so that I can see 2. That is going to go to S5, and S5 goes back to C2. All right. And then finally, at some point, we'll exit out by going to S6. Now, we talked last week about, make sure that, yeah, okay. We talked last week about that the number of regions plus 1 was this cyclomatic complexity. So that would be 1, 2, plus 1 is 3. So the cyclomatic complexity is 3. And what that would represent would be we want here. This would be a path that comes straight through here, path that comes straight through here, and then a path that takes one of these routes but then engages the loop as well. Okay, and that's what the cyclomatic complexity kind of represents, or it's also what the number of nodes minus the number of edges. No, other way around. Number of edges minus the number of nodes plus 2. All right, and then there was one other way that we calculated. It's listed over here. Right. But the idea is here is we want to figure out, okay, so there's a path that goes through here and just exit out to S6. And then there's a path that goes through here, but then there's also a path that needs to take this loop at some point. And so our P star is going to help us figure out, well, how many test cases would I need to do to, because if we consider that a path that involves this loop, well, you have, what if there's one path that represents the loop is never entered. We never get to S5. The condition's false. The condition 2 is false the first time we come through. Right? And that just goes straight through here and goes straight to S6. Then there's a situation, well, there's a path that is, so maybe if I draw with a color here. So it just goes straight through here. Okay. Then we might say, well, there's another path that represents going through there and going through the loop and out. Right? And then, well, there's another path that goes through the loop, goes back through the loop again, and then comes out. Right? You could see how this could go on, for as many times as we need as many times as this loop could get entered, and it could get really problematic, especially if this loop is something like processing through a classroom full of students, and the maximum number of students in the class is 150. Like my 101 class is 150 students. Well, would I need to write 151 different test cases to test that thing? Well, no, I wouldn't really want to have to do that, right? So, but it is considered, like you said, it is considered what we call an upper bound. So it is somewhat of a max there. All right, so let's go back over here. So the idea behind a decision path, or a DD path. So the idea here is it's about how the program controls the flow between two decision points, between one decision to another decision, and it wants to make sure that all the nodes have been visited at least once. Okay, so the idea here, let me pull it back up. So if instead of here, let's say that from here we had another condition to here that did one thing over this way and did something else over this way. Okay, and and then comes back down to here. Now we could say that, let's say we go through this side the first time, and when this condition is met, we go down this side here this time. Okay. And let's say we also have another test case that goes this side and goes this side. Okay. Now, can we say that with those two test cases, that we have visited every node in the graph?
No, absolutely not.
Okay, well, why not? What node
Well,
have we?
if I follow the green one, I'm not visiting S2 and the S in the down.
Okay, well, let me ask it this way then, because let me ask it this way. Do we have a test case? Do we have every node as a part of a test case somewhere?
Can you please repeat the question?
Can we say that every node in our graph is a part of some test case? Like this red line represents test case 1, this green line
Okay.
represents test case 2. Can we say that every
Yes.
node is covered by some test case?
Yes, we can say that.
Right. We could, and we'd be right. And this is where the DD path, the decision is its concept is that basically we just want to say we visited every node once. It's kind of a bare minimum type thing. So yes, every node is visited once, but the problem could be that what if use a different color? What if something that happens over here in S2 impacts something that happens over here on this side of this condition? We don't have a test case that checks that, right? Right. So this is and so that's a problem because even though we have every node covered, there are certain situations that we may not have planned for that we could end up with having some problems. Okay. So the idea behind the DD path is we're just trying to minimize as much as possible. We just like, look, we want to hit every line of code at least once. And so, but it can result in some problems in that we undertest. Okay. So then the idea would come, the idea of a basis path. So let's look at an example here. So the idea is this is going to connect back to last week's discussion about, well, that even though this is a single if statement, it still kind of represents two different paths. One where this is false, and we just skip out of it. One where, or sorry, three different paths. All right. One where this is false, so we just skip out. One where this is true, but this is false, so then we also get out of it. But then one where this is true and this is true. And the opposite we'll also see here with this other one. So if we unroll it a little bit, so the fact that this has no else, this is why we can do this. In this example, we can see it better. Is that we unroll it a little bit. We say, really, we're only going to get to this line if this is true and this is true. So that might help us better see how when we convert this into a graph, why this condition and this condition could represent two different paths. Okay, and then this one is the opposite. So here, if this is true, then we don't need to check this other one. All right, we just do it. Otherwise, so this is false. If this is true, we do that x is x plus 1, and then we're done there. Okay, so we kind of unroll these joint conditions, these and or conditions, into separate if statements. Okay. So then what we would do is we could take this to convert it into a graph, would look something like this. If now this I should have noted, and maybe I will here. Just noted which one's which. So this is actually the. What is that? Okay, so this is the false side. This is the true. So I'll note the rest of them here in a moment. But so if this is false, we just skip over this line here. Right. Same thing here. Where where we only end up seeing this line if both this was true and this was true. Okay, this, that, let's see, this is the true line here, the true line here. And then 1 is the false here. I don't know, the false there we go. Okay, so we end up only seeing this if if either this condition or this condition was true. If they're both false, we end up over here. And so then when we start looking at the, we talked about the cyclomatic complexity, and the path coverage as well. We see these as distinct paths because we do want to check. So if we go back to this original, much cleaner way of writing it, I wouldn't expect you to write code like this. I would expect you guys to write code that looks like this in this situation. But we do need to see that this, even though this may look like a one true or false condition, it's true in one situation, but it's false in multiple situations. And we do need to test for the different ways that it could be false. We do need to test, what if this was true and this was false? What if this was false and this was, well, we don't care what this is at that point, right? We don't care what the second one is, right? Unless of course you're using the single ampersand and it does check both conditions, right? Then we would have possibly four possible paths in that situation. So some of the terms that I've thrown about this class about the levels of test coverage, the idea of statement coverage would be the idea that each line of code, each statement is executed at least once. Branch coverage, so each decision, we want to make sure that each side of the decision is executed at least once. Some condition, so we want to make sure that that each condition takes on all possible outcomes. So this would be, so branch coverage would be, if we look at this again here, we want to check, what happens with a true outcome? What happens with a false outcome? That's all we care about in branch coverage. Condition coverage would be the idea that, okay, what are all the different condition possible outcomes? So the condition decision would be, okay, what if this is true, but this is false? What if this is true, but this is true? What if this is false and this is true? What if this is false and this is false? So some of those different possibilities. And with each kind of level of like adding more strictness, so again, statement coverage, branch coverage would say, as long as I have one situation, one test case where this was true and one test case where this was false, that's all that matters. Or actually, let me go back. Statement coverage just says that every line of code has to be tested, which means that as long as I have a test case where this is true, then this line of code gets tested and I'm done. So in statement coverage, we could actually write one test case for this whole line of code, for this whole code segment here, and we could have statement coverage. If both, so if let's say A was 2, B was 0, let's say A was 2 and B is 0. Doesn't even matter what X is. We would then have statement coverage. Because if A was 2 and B was 0, this would be true and we would execute this line. If A was 2, doesn't matter what X is, this would be true and this line would be executed. We would execute every line. So one test case would give us statement coverage on this. Right? Which is why we do want to go a little bit more strict, a little bit more robust in our testing, because again, we want to come up with the different ways that this is true. We definitely want to know what happens if this is false, because as we said before, this right here, this x giving a value here is going to impact this here, right? So this x changing its value is going to impact what happens in this line. Right? So we want to make sure those things are covered. What happens if we don't enter this if statement, but we enter this one? What happens if we enter this if statement, but we don't enter this one? So there's a bunch of different paths that we want to make sure we cover. All right. Now, again, all paths covered would be whatever that p star value is that we calculate. It's pretty much generally impossible because all paths become, especially with while loops, with indefinite while loops and all kinds of stuff like that, that it becomes really, really difficult, generally impossible to make sure that we cover all possible paths. Okay. Let's also go ahead and revisit the cyclomatic complexity, because again, what we're doing is we're calculating some of this, some of these numbers that are going to be important in understanding not necessarily what the test cases will be, because we'll have to look at the actual conditions for those condition nodes and some of the values that we're testing and stuff like that. In order to find out what the test cases actually are, we'll need to look at some of that. But this is more just an idea of, okay, I'm going to need to create some number of test cases, and this is going to help me figure out what number of test cases I should be creating from the start. All right, so the basis set, we're going to say, okay, we're going to look at our graph that we've created from our code, and we're going to find the shortest path. So the shortest path here, okay, well, shortest path here, we'll start at the start node. The shortest path here, well, eventually we're going to get to here, no matter what. So what's the shortest path to get from here to here? It's going to be this false line here, right? So my shortest path is this so far. Now, what's the shortest path from here to here? Well, I could go through one node and then there. Well, I could go through one node and then there. So there's actually two possible answers here for what the shortest path would be. So just pick one. So just add that to our set. Right? So we add that to our basis set. Right? And then we find the next path by adding as few edges as possible. So let's see, we want to add some edges. Well, if we took this path, then we could add 2 edges or 2 edges. There's really no way to get around adding something with 2 edges. So we're just basically going to have to add either this node here to get 2 edges, whatever node of these two we didn't choose the first time to get 2 edges. And we just keep doing that, right? Okay, and then we're going to continue until all edges have been added. Okay, but we're just kind of saying what the new, what the next path is through there. All right. Let's see. Let's skip over to this one. Let's talk about some of the test case generation stuff. Okay, because one of the things that we need to acknowledge that when we start creating our test cases is that there are some paths that may not be feasible. For example, there may be a path that involves not entering a while loop, but it's not possible. We will always enter that while loop. Or there may be some path that that represents some kind of condition that we should never see. Like if we look back at, let me pull up this over here. If we look back at this example I gave you here, let's say that something in S2 right, makes it such that this condition cannot be true. Well, then it wouldn't make sense to test S2 followed by whatever that condition is, right? Whatever that is. Okay. So that would be a path that's not really something that we could test. Maybe S2 sets a variable's value in such a way that C2 cannot be true or cannot be false. And so we don't really need to test that side of that path because it's not possible. Okay. Let's see. Some problems when just doing cyclomatic complexity, right? Remember, cyclomatic complexity is somewhat of a minimum because we're just doing like basically making sure that all nodes are covered, all that the paths are generally just basically tested. But loops may not be tested thoroughly, right? And we may not be fully exercising our data structures. We may not be fully realizing some of the higher end values if maybe we have if we have an integer data type, maybe not an int, but maybe something smaller, like a short or a byte integer data type, and there's a possibility that it could overflow or underflow, then we may not be testing fully when we just do the path coverage, when we just do use the cyclomatic complexity. So the idea is, so what should we do for loops? Right. Well, we need to make sure that some of the things that we test for, we need to test for initialization errors, make sure that our variables are initialized correctly. So our iterators are initialized correctly. What if, so an index or incrementing errors, I've seen this happen before. Let me, I'll put a text box in here. I've seen programmers do stuff like this. It just keeps, Microsoft is messing me up. I equals 1. Let me add the for part of this because it's a for loop. For int I equals 1, I is less than 10, I plus plus. All right, so something like this, where they do something like this, and they're expecting this loop to execute, 9 times, 10 times, if I equals 1, 0, whatever, maybe we're looping through an array or something like that. And then there's some code here that does some stuff, and somewhere in there there's like this random if something, and they check some condition, and what they do with that is they like say I equals 3 or I equals 0 or something, where they change the value of I. So this could be like this could be a real problem, right? Because you're not then gonna loop through this 9 times or 10 times or whatever it is. You're now changing the iterator value, and I've seen lots of people do that. Right? I've seen that in code before, and it's not that they're trying to mess the loop up. It's just that they use this variable that they thought, oh, I have access to this variable that's already created. Let me use it as something to do something else with for a little while. Right? And that could be where these index or incrementing errors, or the index is outside of the bounds of the array or something like that. One thing we also talked about we've talked about before is this idea that bounding errors that occur at the loop limits. Generally, these edge conditions, whether it be edge conditions like with the start of an array or a string, the end of, or somewhere where a level is changed, right? So let's say back to this example here, you might have like my array dot length. So this is what the loop should look like, is you go from 0 up to length minus 1, incrementing I each time, right? That's how we would process through the array. You know, what happens if our loop looks like this? Well, if we try to access the array at array.length, right, then we're going to get an index out of bounds error. In most programming languages, not all, but in most programming languages, we'll get an index out of bounds error. And so these are the kinds of things that we need to test for. So then there's some different types of loops: the simple, just single loop; nested loop, one inside of another; concatenated loop, one that comes after another loop. Okay. So how we can test them? Well, testing simple loops is we need to make sure we have a test case that skips the loop entirely. We don't even enter the loop at all. We probably should have a test. We definitely need to have a test case where there's a entry of the loop, period. Okay. Now, if we say that we need to test all these different conditions, what about 2? What about n? Right, passes through the loop. What about m minus 1, m, and m plus 1, where m is the maximum number of loop iterations? So these are the types of possible things that we want to check. We want to make sure that we have a situation accounted for where the loop wasn't entered at all. We should have a situation where, what if we only went in there one time? What if we only went through the loop and then exited? Okay. Make sure that we were able to go through the loop again. Right? N passes through the loop represents the expected normal number of times that we would go through the loop. Okay. So, you know, it's not necessarily the maximum, but it is, you know, could be. You know, it's the what is most likely to be the number of times that we need to pass through this loop. And then finally, whatever the m is, the maximum number of loop iterations, we need to know, okay, what happens if we get right up below that? So if the maximum number of times that we will pass through the loop, if it's based on an integer value, right? Okay, what if it's a 128? Right? Do we have a situation where we go through the loop 127 times? What happens if we go through it 128 times? What happens? Do we expect an error if we pass through the loop 129 times? Right? What is our how do we handle a situation where if something happens to cause us to be able to go through the loop more times than we expected the maximum to be? Okay. Does it generate an exception? Does it generate an error? Does it do it anyway? Right? Okay. For nested loops, we want to, whatever the minimum is for all the outer loops, be 1. We do a simple loop test for the innermost loop. Okay. And then we work outward. We then test the outer loop, the next outer loop. Right. And we just set the inner loops at the typical number of iterations, whatever n was. So once we make sure that those inner loops have passed our test cases of skipping 1, 2, n, and m's, then we go to the next outer loop and we do the same thing again, and we keep any loops that are outside of that at just 1. We enter the loop. And for this loop that we're working on, we go through this process, just skipping it once through, twice through n and m's. Okay. And then we just keep doing that until it's finished. Concatenated loops, if they're independent of each other, so one's outcome doesn't affect the other, then we just treat them as 2 simple loops, and we test the one, then we test the other. If they are dependent, however, if what happens inside of the first loop impacts what happens inside of the second loop, then we look at them as nested loops. Okay. Unstructured loops, I'll give you some information about what those are. but we don't want unstructured loops. I think those are the where we use like break and control statements and go-tos and stuff like that, which we shouldn't use those because those are very difficult to test. Okay. One more thing that we do have, and there's some examples that I just gave you of this DU path, this data flow path. It's the idea that instead of necessarily finding this path situation, what if we instead say, well, what about the data flow instead of the control flow? So this whole path testing is based on control flow. But data path testing is more about, well, there's a variable inside of here, and its value, it's not used here in this first if statement, but it's used here in this second one. And so I don't really care what happens in the first if statement based for this variable. I really only care what happens down here. Right? And so the idea is to come up with information related to how data in some of these nodes is affected by that same data value, that same data item in another section. Okay. All right. So if we look at these examples that I've given you guys, let's go back to the 9H one here. So now you should be able to calculate this P star. So we went through this last week where I gave this example 1, question 1, where I took this, right, and I said draw the graph and calculate the cyclomatic number. So we talked about that last week, and I said we would talk about P star this week, and we have now. So if we assume the while loop at line 5, so this thing here, executes exactly 4 times, okay, then according to the way that we calculated that P star, so let's start just down here, right? So this path, there's one way through this side, there's one way through this side, so we add them together. That's what this 1 plus 1 is. Okay. Now, this 1 plus 1 is 2, is indicative of a loop that we said would go through 4 times. So what we do is bring that to the power of 4. So 2 to the power of 4, 16. Now that 1 times 1 here, that represents this node before, right? And this node after. So that's this portion and this portion. These are each considered 1. So this would be 1 plus 1 to the power of 4 is this loop times 1 times 1. Okay. Times 1. Then we multiply it times 1 for 3. It's really a lot of extra multiplication by 1s here, but really the main thing that we understand is the driver of this loop, the driver of this P star is, let me see, there we go, that's better, I think, is this loop here and with an if statement inside of it. Because what we end up with, we end up getting back to this plus 1 out here, and that is this side over here. So this whole thing over here was that 16. And then this is 1. And because there's a decision here, we add them together. So 16 plus 1, 17. Here, this one's a little bit more difficult because there is this do while statement in line 5. Loops 1, 2, or 3 times, and that's this while was in line 11. So if we pull up here, the while for the do while is in line 11. So that's where it goes back to here. Okay. So if we start down here at the loop portion, okay, let's see. We have this 7, 8, 10 is one side, so that's 1 plus 7, 10 is 2. So that's 1 plus 1 is 2. Inside of the loop, so it's 2 to the 1 plus 2 squared plus 2 cubed. So that would be 8 plus 4 plus 2, 14. All right. Well, the main thing is on this other side over here, as we have this condition that results in 1 plus 1 is 2 on this side. So now we have 14 on this side, 2 on this side. We add them together because they are each 2 side paths of this condition at line 3, and we get 16. Okay. So then I'll let you guys look at problem 3. I do want to go ahead and talk about this du path stuff as well a little bit, and then we can call it a day if there's no questions out there. So the idea here again is, instead of looking at each of these as a segment, as a node in a graph, we're gonna say, okay, what do I need to know about where this is used? So we create this variable called price. Now, by the way, this is not Java. This is C code. Okay, if you've never used C before, it's a little bit different. Okay, so price is declared here. It's used here, but it's assigned here. Okay, now it's part of this if condition. It's part of the inside of this if condition in both of this line and this line. It's part of this if condition. It's part of this inside of this line and this line. Same thing here, 20, 22, 20, and then it's here, but it's not used here in 25. So here, what I'm going to do is I'm going to put these side by side. Okay. So it's a little bit easier to see what's going on here with this example. Okay, so what we're saying here is, okay, we have a table, this use table and path table. The use table is going to tell us, okay, where it's defined, like one here. So in C and Java, unlike some other typed languages, you have to declare and give a value to a variable. So here, its definition is given in 4 and 8. So 4 is where it's declared, 8 is where it's assigned. It's never given any other definitions, like it's never given a new value somewhere else. Benefit is a little bit different. Benefit, it's declared in line 5, but it's possibly assigned in line 12. It's also possibly assigned in line 18. It's also possibly assigned in line 22. Discount, declared in line 6, possibly it's assigned in line 11, also assigned in line 17. Where is it used? Well, price is used in a lot of places. We talked about all these different places that are using if statements and assignment stuff here. Benefit's only used in one place. Okay. Discounts used in multiple places. The reason why this becomes important is then we need to talk about what the the definition use path is. Because instead of being this node, because the truth is, the value, benefit here, you know what? It doesn't really, like, as far as what its value is, when we use it, it only matters what it is once we get down to here. So we don't necessarily need to talk about the possibility, the path of if it goes inside of this if statement and then it also goes inside of this if statement, because notice that these are mutually exclusive if statements. If we go inside of this if statement, we can't go inside of this one. Okay. I'm getting a little bit out of my head a little bit. Let's see. All right, so the different possible definition use paths. Notice here we have one DU path that says, okay, it goes from 8, where price is defined, to 9, where price is what is it? Where price is used. Okay. Now we want that. We could say, okay, it ends there. So price, the whole idea of it ends there. Now we are going to eventually get down to 24, right? So we do end up needing some path that gets us down to 24. Now, notice the path that we're getting to is this. It goes inside of this if statement, all right? And then it goes 8, 9, 11, 12, all right? And then there's a path where it goes 8, 9, 11, 12, 15, and it ends there. 8, 9, 11, 12, 15, 20. 8, 9, 11, 12, 15, 20, and ends at 24, and that's where it's done. 1 second, hold on just a second. Let's man the door. Okay, sorry about that. Sorry about that. So, maybe a better one.
It's okay.
Maybe easier one to look at here would also be this benefit one. Okay, where here one possible path is we are going. Well, it shouldn't be 5, 6. 6 should not be included. It should be 5. Oh, okay. We go through. I see what they've done. We still got to go through those lines of code to get there. That's what it's talking about, this path. So 5, 6, 7, 8, 9. Then we skip over that and go 15. All right. Then we skip over that and go 20. We skip over that and go 24, 25. Now, this is where it goes. It's defined here, and it never sees another definition statement. It never sees another line where it's given a separate value from its initial value. By the way, in C, this does not give you a compiler error. It would give you a compiler error in Java. It doesn't give you one in C because C gives default value, so the default value would be 0. So here we say, okay, well, this is if we have an initial definition and we never have another definition and we just go to the end. Okay. This is, we start at the second place that it's defined, 12, this one. We never have another definition. So we go to 15, we skip over and go to 20, we skip over and go to 24 and 25, and we go to the end to the last time that it's used. This is, okay, well, what if it's defined here? This is where it was defined, and it never sees another definition, and it goes to the, and then finally this one, what if it's defined here? It doesn't see another definition statement, and it goes to here. Okay. So in each of these situations, we're saying, okay, it's defined, right? We want to have the path that gets us from its definition, and the definition, so for these purposes, for the path table, is where the value is given. So here for price, no value is given here, the value is given here. Here for discount, given here, the value is given here or here. But it could also be no value at all. It could also be just the no value at all, but just the initial, the default value. Okay. So we want to say, okay, start from the definition and go to every possible last use, and just make sure that we get there and make sure that we have something that covers that. So here, defined at 8, and we get to 9. How do we do that? Okay, define at 8, get to 11. How do we do that? Define at 8, get to 12. How do we do that? Define at 8, get to 15. Define at 8, get to 17. We have that? Yeah, because that's where it's used. All right, define 8, get to 17. Define 8, get to 18. Define at 8, get to 20. Now there's a couple of different ways we can get there, right? There's a couple of different ways that we can get to 20 from 8. So we need to cover both of them. Define at 8, get to 22. Right there. Define at 8, get to 24. We have that in a couple of different ways. All right, in 4 different ways. Here, define at 5, get to 25. Now notice there's only one place that this is used. So basically our 4 definition use paths are going to be where it's defined, where it's used. So make sure we have a situation where it's defined here, and how do we get straight from there to there, straight from 12 to 25 without it being defined again. 18 to 25, right here, 20 to 25, right here. And finally, discount. The thing about discount, though, is it's always used in that very next line. So here, it's defined in 11 and it goes to 12, or it's defined in 17 and it goes to 18. There is no possible way that it could be defined in 17 and get to 12, right? There's no way that it could be defined in 11 and get to 18 without also going through that other definition at 17. Does that make sense? I mean, this part's a little bit confusing, I think, but basically at its core, what this whole definition use idea testing, at its core, what it's about is, instead of necessarily saying, let's make sure we test all the paths, let's make sure we test all the lines of code, it's more of the idea of saying, this data is defined here. Let me see if I can make sure I understand how it's used later. And make sure I understand the different ways that it might get changed. So again, in an example, here, we don't test something that involves going through line 11 and line 18, because it can't without 17. Like, so we don't worry about discount being defined here and then used here. We worry about discount being used here and being defined here. It's the nature of how sequential code works. All right, so I gave a lot of new, gave some new examples here, gave some new ways of looking at this. I know it can be a little bit overwhelming, so excuse me. So what is confusing? What is questions here?
Well, I would rather this be in not in a list form, but I think the list representation is the confusing part. The
Yeah.
the logic is easy, but I don't know, maybe there are other representations as well instead of a list.
Yeah, it could be. It's basically what it's trying to do here. If we look at this one here, what it's trying to say is, okay, we want to get from the definition, we want to make sure that we have something, some test case that acknowledges that we got from 8 to 9, that we got from its definition to its use somewhere. Now, some of these are kind of like overlapping. So, for example, where is it? Here. So, for example, this 8, 9, 11, and this 8, 9, 11, 12, you know, really, hold on, this is like, there we go. Like these two right here, these two DU paths, we could kind of look at them as being the same. All right, in the sense that it is unlikely that we would get to 11 and experience some kind of error that would prevent us from getting to 12. Right? It's highly unlikely that that would happen. So in a sense, we could say they are the same. But the idea is we want to make sure that we have some type of path, some type of test that covers the situation where we have a variable defined, and then we understand that we used it. So we want to make sure that we defined it, we gave it a value, and that based on that value, we got to this line of code. We got to these lines where that value is used. And so if we write it out here, this path, then what that helps us do later is write out what the test case should be. So if we say, okay, this is the path that I'm covering. This is the data use path that I'm covering. What would our test case have to be in order to cover that path? What value would we need to give to what variable? Anyone? So we want to make sure that we cover, and I'm counting for the purposes of testing, I'm counting both this revised number 2 and 3 as being the same one for the purposes of testing. So what does our test case need to look like?
Uh, I don't know how to answer that actually.
Okay. What value for what variable? What value for what variable would follow this path that I've highlighted here? This 8, 9, 11, 12.
It's the price, isn't it?
Right. And what value would we need to give to price?
To follow it, it should be bigger than one. How many zeros are there? 10,000,
Right.
right?
Right. So we would want to make sure we have a test case that in order to cover this data use path, we would need to have a test case that involves price being greater than 10,000. So 20,000 would do it. 10,000 would do it actually because it'd be greater than or equal to. Right. So then when we start looking at some of these other aspects, again, what we're doing is we're saying start at this definition value, this definition line, and give me a path, a data use path that terminates, that ends at every possible use situation. So notice that the black ones here in the original solution for this, the black ones always just take the shortest path to get there. So we go 8, 9. So to get to 9, we just go 8 straight to 9. To get to 11, we go 8, 9, 11, because we have to go through 9 to get to 11. In order to get to 12, we go 8, 9, 11, 12. Now, as I said, the black ones just take the shortest path. So to say, okay, I want to go from 8 to 15. Well, I need to go 8. I need to go through 9. I have to go through 9. But I don't have to go through these. All right. I just go 8, 9. This is false. I go to 15. Now, to get to 17, all right, if I'm following the black ones here, 8, 9, 15, 17, there is no path that gets me to 17 through 11 and 12. All right, because these are mutually exclusive, because I cannot enter this if statement and also enter this if statement. All right, so 8, 9, 15, 17, 8, and then to get to 18, 8, 9, 15, 18. These blue ones here added this, the fact that for, say, for 15, which is an if statement, it is possible I get to this if statement by going through the inside of this if statement first. I can't go inside of this, but I could go through these two lines and come out and still have to see this if statement. Okay, so that's what the blue ones are. The blue ones are more kind of adding that, well, you know, I mean, I guess I could go through here and still get to this line. Right, but that's being more kind of specific. That's being a little more nitpicky. Right? The main thing about the definition use path is we're trying to say, okay, I want to make sure that we acknowledge the paths that get me from here to every place that it is used. So I need to have a path that starts where I give it a value and ends where it's used somewhere. It starts and it's used, it ends there. It starts and it's used. It starts and it's used. 15, I have something that gets me to 15. A couple of somethings. I need something that gets me to 17. How do I get there? I need something that gets me to 18. How do I get there? I need something that gets me to 20. How do I get there? I need something that gets me to 22. Wait, how do I get there? I need something that gets me to 24. Right there. In the same way, the benefit is, okay, the benefit's kind of the opposite in that where is it defined? And it's always just used one place. So here, the price, as far as given an actual value, it's only defined one place. So I needed all the paths that started where it was defined and ended somewhere it was used. So all these paths represent starting at its definition, ending at its use. Benefits kind of like I said, like the opposite. Every path should end where it's used because it's only used one place. But all the paths should start wherever it was defined last. So how do I get from 5 to 25? Well, the way to get from 5 to 25 is I go 5, 6, 7, 8, 9. I can't go inside of 9. I can't go inside of the if statement because if I do, I'll encounter another definition line. So that's not going to get me there. So 9 I have to skip over. 15 is the same problem. 20 is the same problem. So notice here I've gone where is it? 5, 6, 7, 8, 9, skip over. 15, skip over. 20, skip over. 24, 25. So that's a path that gets me from 5 to 25. Now I need a path that gets me from 12 to 25. Okay, 12 comes out to 15, but it's got to skip over that, right? So 20, it's got to skip over that, 24 and 25. Something from 18 to 25. 18 comes here, comes out of the if statement, hits 20, hits 24, hits 25. Right, so that's, and then one more, the 22. 22, it's assigned here, it's defined or assigned here. We come out of the if statement and we hit 24 and 25. And like I said, discount becomes a little bit even easier than the benefit one because it's always just used here and then put here. Right? Used here and defined here and then used here, defined here, and then used here. It's not possible that it could be defined here and then used here because the only way we get here is if we go through another definition line. It's also not possible that it could be defined here and be used here because we can't go backwards. Okay. And the idea of what this table is doing is it's trying to make us say, okay, I need to write a test case that accounts for this path. I need to write a test case that accounts for this path and account. So I need to write all these test cases that account for these different paths. Also understanding that when we actually go to write our test cases, that because some of these paths are inside of others, so really in the grand scheme of things, this here would be our test case because it covers all of these. It includes all of these. Okay, but what we're doing is we're starting with, just like with the P star that we talked about, the syntactic paths, just like with that, we're talking about trying to come up with an upper bound of what our test cases will be, of the number of test cases we will have to write is. Because what we want to do is we want to not just, what we're trying to get away from is we're trying to get away from looking at a piece of code like this and saying, oh, I think I should test if price is 10,000. I think I should test if price is 2,500. I think that's good enough. Like, we're trying to get away from the ad hoc process for designing tests. We don't want to just look at a piece of code and say, I think I should test this value. Oh, I think I should test this value. What we want to do is get to more of a structured approach of how we develop our test cases. And by acknowledging, by analyzing the code and analyzing the path of the different ways that things interact with each other, we have a better understanding of what we should be testing and therefore how we should be testing. Okay?
So just a single question. Why
Sure.
we are not including inside of the if lines to the definition use path.
Like which
For
one are you talking
example,
about?
okay, so the one now it's highlighted 8, 9, 11, 12, 15, 20. For example, after 20, why I'm not writing the line 22 also? Let's say
Yeah,
the price is. Uh-huh.
good point.
So
So,
why am I skipping the 22?
right, because if we go inside, if we encounter 11 and 12, it means that our price has to be at least 10,000, which means this would have to then be false. Because if this is greater than or equal to 10,000, the price is greater than or equal to 1,000, it cannot be greater than or equal to 1,000 and less than 5,000. So these,
Yes, but to be sure, doesn't a compiler checks those lines?
now what you're saying is that a compiler, yes, a compiler would not be able to tell us that code could enter here and not here. But this is for us for the purposes of writing the tests for this. So we want to make sure, and this would be a path, so a path that would be impossible would be a path that includes lines 11 and 12 and also includes line 22. That would be an impossible path for our execution to follow.
Okay, so this is for testing cases, and as a student, uh, the compiler jobs is compiler jobs. My job is here to write the test cases only. Now I get it. Everything is very clear.
Yeah, let me draw that one out because you bring out a really good question. I'm going to draw it using flowchart though instead of the graph notation.
Okay.
So if we call this condition 1, 2, and 3, okay, 1, and this is lines 11 and 12. Let's call this actually. Let me give this the 9 label that it's line 9. So this is the true path. This is the false path. Okay. So then we have a condition here. This is line, what, 15? This is 17 and 18. And then we got one more. 20. 22. And then we go on. This one's supposed to be an arrow. Okay. So, if I were trying to follow syntactic paths, path coverage, I might say, well, I need a path that follows here and here and here. All right, I might be tempted to say that. The problem is that if I enter into here, because these conditions are not mutually exclusive, that if this was true, if I followed path 9, it's not possible that I could have done I could not have been true on line 15. If price was greater than 10,000, it's not possible that my price could also be less than 10,000. So therefore, I could not have entered here. All right? And so this path that I've drawn out is impossible. I cannot write a test case that follows this path. Right? And that's somewhat of what kind of that data use kind of helps us understand, can help us understand, is that we're looking through here. Yeah. So we're looking through here to see how this data is defined and then how it's used later, and can it be defined again, or can it be used based on what these conditions are. This would also be something that I would tell my first year students. You should not do this. You should do an else. Because if you know for a fact that this and this are mutually exclusive like this, then what you should do, you should just do an else if here. But, you know, that's not everybody writes perfect code, right? So yeah. So if we were writing, if we needed this for an industry job somewhere, yeah, I would definitely say instead you should write something like this, where you have a true lines, and then you have an else. 15. You have an else. 20. Right. And they all, I guess I should think this way. They all link up at the end, right? It's all a bunch of if else's instead of a bunch of if conditions, right? This would be a much better representation. This would be a much better way of using the else's instead. So, all right. So that's how you do
I
those
get
data
it.
use stats. I will probably not give you guys an assignment on the data use stuff here because, like you said, it is quite a bit more confusing. But I do want you to go ahead and at least have a knowledge of it. Knowledge that this whole path testing we talked about, the syntactic paths, the cyclomatic complexity, it's all based on kind of the control flow idea, whereas the data use testing model is more based on the understanding that how data flows through the program is also important. All right. Well, if does anybody else have any other questions, or Alper, do you have any other questions?
No, everything is clear. Thank you very much for the lecture.
Yeah. Well, thank you guys for attending. And yeah, so now you have all the tools that you need to be able to do that assignment one. I know it's a little bit late, but assignment one technically was that paper that you guys wrote. So technically, I guess this is actually the second assignment, but it should be pretty straightforward. It shouldn't take you long. Just follow kind of the example that I did here in class or in the meeting. So, all right. Other than that, have a good weekend and enjoy more
You too.
lockdowns. Enjoy more lockdowns, right?
Yeah, stay safe. Stay home.
Yeah, you guys too.
Okay. Thank you very much.